So we're back. So, which is just as well. So, let's talk about a model of electrical conduction. And we're going to do a conceptual visualization. So we say, assume that a conductor is a rectangular array of atoms. So what that means is it's like, basically in 3 dimensions. I'm going to draw 2 dimensions, but it's like that. It's, plus a collection of free electrons. So here's some free electrons whizzing around. In the absence of an electric field, the conduction electrons move randomly through the conductor. And in the absence of an electric field, there's as many going in one direction as the opposite, so there's no overall effect. They're moving really fast, but there's no overall migration because there's no field. It's like blindfolded people running on a level playing field. There's a chance they could all run to one goal, but if you have enough of them, that chance gets incredibly small. They're just going to run around and bump into each other perhaps, but they're not all going to go one way or the other. Yeah, but if you had them on a slope, they'd all end up at the bottom of the slope because that's human nature. You kind of run downhill. So that's an electric field. That's what the electric field does. They're going really fast. That's really fast. That's 1,000 kilometers per second. They're not slow. They've got thermal energy and they are next to no mass and they are flying. In the presence of an electric field, then the conduction electrons still move randomly, but also drift. So what happens is this guy goes with the field, and this guy goes with the field, and this guy goes with the field, and this guy goes with the field. So they all end up heading towards the right on my diagram. They run into things, so this guy might run into this guy here, and then it bounces, and it does that, and then this guy bounces and does that. So, but there's this overall drift. In the presence of an electric field, the conduction electrons still move randomly, but also drift in the direction that is opposite to the electric field because, of course, they're negative electrons, so E is in that direction, and the little electrons are moving in the opposite direction. The drift velocity is about 10 to the minus 4 meters per second, so it's a tenth of a millimeter per second. Because there's so many collisions, and it's just the way it goes. The conduction electrons gain energy between collisions, just like a bouncing ball would, but lose energy on the collision because it's giving energy to the atom. The energy given up during collisions causes thermal energy, causes temperature rise. You're literally colliding these energetic electrons with the atoms, and they get hot because they get energy from these things. Here's some math of it, and I'm not being funny, but we're getting to the stage where we're getting so much material that I'm going to pick my battles. So I'm going to go through this, but basically the force on an electron is equal to Q times E, and F equals ma, so A equals Q times E over M. And if we bring in our kinematics, Vf equals Vi plus At, well, Vf equals Vi, and A is Q times E over M times T. And we can define the time constant between collisions. On average, how long does this thing go between collisions? We call that the time constant, tau. And then if we bring in our equation for the current density, then we can say conductivity is equal to the current density over the electric field, which equals nq squared tau over m. And the resistivity equals 1 over sigma, 1 over this conductivity, m over n qt times tau, and q squared times tau. And I don't really care about that. I'd like you to know it's there, but I'm not going to ask you a question about that. Okay? I might conceptually ask you about, well, what happens if you were to picture what happens when an electron goes through a piece of wire under the influence of a potential difference, but that's about all. This is more important, and there's really only one equation here. There's the resistivity version of it, and there's the resistance version of it. And basically it says over a limited range of temperature, the resistivity of the material changes linearly with temperature. And this is basic. It doesn't look particularly like it, but this is a linear equation. So the resistivity at a given temperature is equal to some standard resistivity, 1 plus alpha. Alpha is the coefficient of thermal resistivity, the temperature coefficient of resistivity, the temperature that you're at minus the original temperature, standard temperature. So you learn that, because when you know that, you can say, well, my resistance at a given temperature is equal to my standard resistance, 1 plus alpha. It's the same alpha, temperature minus the temperature. What temperature should it be in? It turns out that because it's a difference, it does not matter. No, I'm sorry, I've got to be more careful with that. It's taken care of by your alpha, your units for alpha, as we'll see in a minute. Okay. A material has a resistivity of 4 ohm resistivity, 4 ohm meters at 20 degrees C. It has the same material as a resistivity of 9 ohm meters at 30 degrees C. What is the coefficient of resistivity of the material? So I'm going to say resistivity is equal to, what was that equation? What is it? Resistivity. Pardon? I just can't hear. Open brackets. 1. Pardon? Plus alpha. T minus T naught. To the force? No. Okay, just that. So then we say, well, our resistivity equals, let's make a list. It's always useful to make a list. Material has a resistivity of that at 20. There's my rho naught, 4 ohm meters. T naught, 20 degrees C. Resistivity R, 9 ohm meters. T, 30 degrees C. So now I come along here and I say 9 is equal to 4, 1 plus alpha, 30 minus 20. 9 is equal to 4 plus 4 alpha times 10. 4 plus 40 alpha. 5 is equal to 40 alpha. Alpha is equal to 5 over 40, which equals 1 over 8, which equals 0.125. Now, what are the units going to be? Let's think about this. This is going to be rho equals rho naught plus rho alpha t, rho minus rho, that's rho, over rho t equals alpha. I'm just rearranging. Alpha is equal to 1 over t. My units are going to be 1 over my temperature. What was my temperature in? Degrees C. Degrees C minus 1. So not bad. And I could do the same thing for resistance. Bit of a change. So now we're hopping. This is where we start hopping we become physics 2 as periods. Physics 2 has periods where it becomes, do you know that equation? And people either get the question right because they know the equation, or they get the question wrong because they don't know the equation. There's other times when, do you understand this sequence of events, but at other times it's just do you know the different equations. So we have a lot of different topics. So here's a slightly different topic. So we're going to talk about electrical energy and power. A battery converts chemical energy into electrical energy. Electrical energy lost by the battery is converted into other forms in the circuit's components. Could be sound in a speaker, could be light in a light bulb, could be heat in a resistor. A 10-volt battery provides 10 joules of energy per coulomb of charge that flows. If during an experiment 4 coulombs of charge passes through a simple circuit before returning to a 6-volt battery, then 24 joules of energy was. So you say, well, 6 joules per coulomb, that's volts, is equal to 6 joules per coulomb times 4 coulombs is equal to 24 joules. Does that make sense? So my energy is equal to Q times delta V. Yeah. Potential difference of a 6-volt is dropped across a resistor. How much electrical energy is converted into thermal energy when 8 coulombs of charge passes through the resistor? Can you do that for me, please? I'll put some answers up. Can you do that for me, please? A will have as 24 joules. B will have as 0.75 joules. C will have as 1.33 joules. D will have as 14 joules. And E will have as 6 8 48 joules. Bring in all the mathematical changes. Which is it going to be? I'll get you a thing so you can vote. Oh, excuse me. Let it go until 60 seconds. Because you know we don't finish until 10 past. Cool. Most people are saying E, that's the right answer. Yeah, we just say, okay, we say the energy is equal to Q delta V, which equals 8 times 6, which equals 48 joules. So nice and easy. Power. Power is the joules per second. It's the rate at which you can do work, expend energy. I had a conversation, so my brother's an electrical engineer, and we've kind of had parallel careers on different sides of the Atlantic. He's definitely an engineer, and he's worked in business as an engineer, and I've kind of been on the physics side. I've worked in engineering departments, but it was a materials science, an engineering department, not a mechanical engineering or electrical engineering department. And then when I went to North Carolina State, it was still a materials section I was most closely assigned to. So not what you might call your bedrock engineering departments. And when I talk to my brother sometimes, we have completely different ways of talking about the same thing. And even to the stage where he'll use terminology I'm not familiar with when he's talking about motors especially. He's like an expert in motors, so he really, there's a whole vocabulary. There's clearly a specialization there, which he is part of, that as a generalist I'm not part of. But fundamental things. One day we're talking, and he said to me, you know what the difference between a physicist and an engineer is? And I said, what? And he said, you think in terms of energy, whereas we think in terms of power. And I never really thought about it. But you know, what happens for physics studying is you begin and you're doing all your kinematics and the like. And then you get introduced to energy, and after a while you realize, I could have done all this stuff with energy. I didn't need all that kinematics. You know, I could have just worked in terms of initial energy, final energy. I'd have got the same answers. And in fact, there's a school of thought in physics teaching that forget the kinematics. Who cares about it? VF equals VI plus AT. Just figure it out from energy. You don't need that stuff. And there's a sense that it's not physics, it's just bookkeeping. It's like, you know, trivial stuff on the side. There's no principles there. And I thought about, well, I know that as my career's gone on, I've got more and more respect for energy as being an insightful parameter. I never really thought about power. It's just the thing you do afterwards, you know. And from my brother's point of view, he says, it's like this. I ask you, can you build the pyramids? And you say, sure. Yeah, you got a job for 5 generations. What I want to know is, can you build it for next week? That's what the customer wants to know. So I need to know about power. All you care about is energy, and it's so right. I think there's so much truth to that. So we tend not to emphasize power anywhere near as much as we should do. And I find it sad because I will give people questions, and they know the physics. I'm just asking them, I'm playing around with power, and they get confused about it, and they often give away points on this. So let's just be clear. First of all, P is power. It is not pressure. So make sure you're clear about that. Power. And power is the change in energy over the change in time. Well, I know that for a electrical system, the energy is the charge multiplied by the potential difference, which is dq, or delta q multiplied by delta v over delta t. You see, and then I turn around and say, well, delta q over delta t is my definition of current. So I say, oh, P is equal to IV. Let's be careful here. V, delta V, is equal to IR. That's Ohm's law. And P is equal to I delta V. And then we just had that delta U is equal to Q delta V. So make sure you separate those equations. And I learned this as watts equals volts times amps. You know. Okay. If we remember Ohm's law, then we can say, well, P equals I delta V, which equals I squared R, which equals V squared over R. Again, 3 equations, but there's not really 3 equations, are there? There's really one equation. We're just rearranging it. We're substituting in. If we get this, and then we just rearranged delta V equals IR. That's what we're doing. We're substituting that into there, and we're getting these guys. Couple of insights. No, it doesn't matter. A couple of insights. No, let's go. Current of 6 amp flows through a 5 ohm resistor. So I'm going to do this. I'm going to go. Might as well get used to it. So I equals 6 amps, 5 ohms. What power is dissipated? P is equal to I delta V. P is equal to 6 times, oh, no, which equals I squared R, which equals delta V squared over, I might as well practice a little bit. So this will be 6 times 5 squared. So P is equal to 25 times 6, 150. And what will the units be for power? Watts, good old watts. Am I right on my math on that? Let's look. I squared R. I is 6. Oh, I'm not right. Yeah, sorry. So it's going to be I squared R. And what I did was I did I squared R. So it's 360 over 2 times 10. It's 360 over 2, which is 180. Is that not right? Not bad. A little alarm bell was going off in my head, so. Yep.
So the V should be an R?
No. It's, I'm using that equation. But what I did do was I substituted the wrong numbers in.
Okay.
I squared the wrong thing, if you like, yeah. Cool.
Yeah.
So, let's make it a bit more interesting. Okay, that's the power. How much energy is dissipated by the resistor in 2 minutes? Let's do this. Let's say it's going to be 90 joules. Let's have 360 joules. Let's have 120 joules, and let's play with this. Let's let's have 21600 joules. A, B, C, D. And if you know me, you know the answer. So what's the answer? So how are we doing? So you know the power. What's the energy dissipated, the heat given off, if you like, in 2 minutes? We're running out of time now, so I'm going to cut you off. Let you go to 40. Come on, have a vote. Come on. Mainly D, and it's basically what I'm trying to catch you out on is energy is equal to the power times the time. Why? Because power equals energy over time, or work over time. That's my basic definition, so rearrange it. But my power, yeah, that's 180. But my time cannot be 2. It's got to be in seconds. So 180 times 120. So that's where that comes from, yeah? And I can't tell you how many times in a test I'll see people multiplying by 2. Oh! So there we have it. So next time we will deal with simple circuits.